So today we have Krishna Murthy with us from the University of Montreal, and I'm really excited for this talk. Krishna is a PhD candidate at the Robotics and Embodied AI lab, working on differentiable adaptations of physical processes, including computer vision, robotics, optimization, and among others. Which he applied in modern learning pipelines. So it's very groundbreaking research that you're going to hear today. His work has been recognized with NVIDIA Graduate Fellowship, and Krishna has won Best Paper Awards from Robotics and Automation letters as well. He was also a participant in the RSS Pioneers, which is a good segue. So today, Krishna will be talking about a project called Taskography, which is about evaluating robot task planning over large 3D scene graphs. This work was presented at Coral this year, just a few months ago, or last month. And you can check out the amazing webpage that this project has for all the documentation, including the code. So I'm very excited to welcome Krishna today, and I'm going to stop my screen share.
Yeah, thanks so much, Patricia, for the really wonderful introduction and also for inviting me in the first place. I'm just going to set up screen share and just get started. Okay. Just trying to make sure you can all see me and hear me.
Yes, all is perfect.
All right, great. So yeah, it's nice to be here. And I know this time of the year is when things are pretty hectic if you're perhaps a grad student. End of semester is always a pretty crazy time. So hopefully you're coping up with end of semester. And yeah, today I'm going to be talking about some recent work that we presented at Coral last month. And it's called Taskography. And I'm going to be talking about robot task planning and 3D scene graphs. And if you haven't heard these terms before, we're going to spend the first few minutes of the talk just going over these. And hopefully by the end, I'll have time for more open discussion. But if there's any quick questions, you just need clarifications or so, just feel free to post them in the chat or raise hand. And then I'm monitoring chat, so I can probably just interrupt and answer any quick questions thereon. So this work again was jointly led with Chris Gia. At the time, he was an undergrad at University of Toronto, but now he's recently started a PhD at Stanford. And there were a number of supporting collaborators that I'd like to mention. There's Mohammed Khodir, who's again an undergrad at the time at U of T. And we had Andra and Vibhav from Microsoft Research, Mustafa from Facebook AI Research at the time, and then Liam and Florian are the two advisors. Liam's my advisor, Florian's Chris's advisor. So yeah, this was about almost a 1-year effort. So let me just dive right in. But before I get into details of the paper, I want to give some context about my research interests and how I actually ended up working on this. So as Patricia mentioned, I'm with the Robotics and Embodied AI lab at Mila, UDM. Mila is a much bigger group than you see here. There's just a subset of people that work in robotics at our group. And over the past few years, I've been working on a number of themes. So I've worked on perception for autonomous driving. This was again back during my master's. And for a while, I did some work on state estimation mapping. And more recently, I've been thinking about, with ML taking center stage, a lot of applications, including robotics, how do we best somehow bring the best of both modern machine learning systems and classical robotics? Like, do we forget or discard everything that we know about classical robotics and replace them with ML pipelines? Or do we somehow try and blend both of these to get the best out of both? And my research treads on the boundaries of the latter. So in this talk in particular, I want to talk about task planning. And task planning for robots has multiple interpretations. I'm just going to spend 5 minutes setting the right context for what I refer to as planning, and just a few assumptions that we will make for today's talk. So when you see robotics applications, you can see a variety of robotic applications here. There's outdoor applications like cars driving around in a city, or there's like tabletop robots that they have a static base and they need to move around and manipulate objects on the tabletop. Or you have robots that walk around, robots that are mobile and also need to manipulate a lot of stuff. So in all of these, if a traditional view of all of these robotic systems has been decomposed into like 3 major components. So you have a robot, and you can think of this as having 3 major subsystems that enable it to carry out tasks in the real world. So there's the perception subsystem, which takes in data from all of the sensors that a robot has and builds some model of the environment. And we'll dive deeper into a discussion of what kind of environment models are more suitable for a few tasks of interest. But just to think of this as a black box, a perception module will take in data that a robot sensors take in and then builds a model of the environment. And then you have planning, which basically takes into account all of these environment models and some notion of the goal that the robot wants to achieve, and then comes up with a broad or a high level plan of how to get there. So for a self-driving car, it would be what would be the route I take to get to a particular destination. And then you have the low level control module, which actually generates the steering commands, or for a legged robot, all the torques and so on. So one aspect that I've been very intrigued about over the course of my PhD is how can we design models of the environment that are somehow amenable to downstream tasks. So task-driven scene representations, I call them, are how do you take in a scene representation that is just aggregated from a robot's sensor measurements and convert that into something that is more compact and more effective for task planning. And again, as the one phrase summary says, we need to learn map or scene representations that cater to downstream tasks. And a few reasons we want to do that are, they're pretty intuitive. If you want to think about how we as people working in indoor or outdoor environments have this really nice sense of streamlining everything that is not related to a task. So for example, if all you need to do is get from your apartment to your university or your workplace, you'd probably not worry about all of the tiny objects that you encounter along the way. So you don't need a very dense representation of everything that's on your tabletop or everything that's along the route you're taking to your particular workplace. So as a very similar example, if you have, for example, this fetch a mug from the kitchen task for a robot, you probably don't want a robot to reason about every single object in the house, because all you probably care about is things that you're likely to encounter on the way to your kitchen, and you should probably not bump into them and still be able to find a feasible path to the kitchen. And once you get to the kitchen, you only need to care about all of the objects or all of the parts of the environment that lead you to successfully retrieving a mug. So everything else, things that are just stuffed into refrigerators, into other shelves and so on, those are things you need not care about. And with this hypothesis, we were trying to see how you could, for example, build environment representations for robots, household robots, that would kind of emulate this reasoning behavior in humans. So can you somehow discard everything that you do not need for a task and retain only the most relevant attributes? And the reason we want to do this will become quite clear when we start looking at how modern task planners behave. But the core idea is, since you have very few things to reason about, you're more likely to get faster plans to execute a particular task. And these plans are likely to be more effective compared to reasoning over the entire environment. So some of these aspects, I've been interested in some of these aspects even in my prior work. For example, in autonomous driving, we were looking at how you could perhaps think of the environment as a 2D plane and divide it into lanes, vehicles, and so on, which allows for a more fine-grained reasoning of the scene as opposed to directly reasoning over images. And more recently, not so recently though, this was early in 2019, back when we could still run a lot of experiments outdoors. This work was led by Teddy, and this was again an autonomous driving example where we wanted to somehow abstract an environment to make it more amenable to autonomous driving. Currently, a lot of autonomous driving approaches rely on very dense maps. And if you want to build really dense maps of a city or a city block even, you probably need a lot of gigabytes of storage. And one aspect that we wanted to leverage here was, as humans, when we navigate, we don't really care about every tiny detail in the environment, but rather we break the overall task or the route into a few waypoints. And typically this is done in the form of intersections. For example, if you want to navigate your driving, you typically get instructions as at the next intersection, take a right turn and then skip 2 intersections, then take a left turn and so on. So we wanted to see if we could just take a weak topological map, a map that's annotated just to the level of intersections, but not metrically accurate. And we have a plan at the topological level, when to turn right, when to turn left, when to go straight, but you do not know at a metric level how the intersections are spaced out and what's between them. So until you reach a subsequent intersection where you need to replan, you can purely reactively just keep avoiding obstacles, and as long as you can safely keep moving around, you keep doing that. And with this kind of a system, the advantage was you could fit the whole topological map of the continental US into about 80 megabytes of memory, which is something you can actually store in RAM, not even disk. And this was particularly useful because more than 70% of the roads in the US, they're actually rural roads, and their map maintenance becomes really complicated because vegetation keeps growing or gets affected throughout the year. So this was one way in which we could abstract maps for autonomous driving scenarios. So when you usually talk about driving, you have a largely one-dimensional task specification. The task specification is do not crash and get safely to a particular destination. So with this in mind, we wanted to see if we could do something for indoor environments where you could arguably define a wider range of tasks, and there's a lot of potential actions you can take on objects, including just interacting with these objects and perhaps manipulating them. So I'm going to get into some formalism about how we view task planning, and then I'll talk about popular scene representations for indoor environments, and then I'll begin to talk about Taskography, which is our recent work that we presented at Coral. So about 5 minutes ago, I kind of went through this 3-phased pipeline. For most robotic systems, you'd have a perception block, which would perceive the environment, create an environment model, and there's a planning block. That's what we're going to talk about for the remainder of this talk. And the idea, the goal of the planning block is taking a representation of an environment. So you assume that you already have a perceptual representation of the environment, and then you want to figure out how you execute the task at hand. So here, just for formally defining a planning problem, your environment representation is a graph. And let me just talk through what the graph is. So there are nodes in the graph, which are objects in the environment. So they could be objects you can actually pick up and move around, or they can also be objects that you cannot move around, like a building, for example. That's also a valid object to have in your graph. And once you have objects, you have a set of properties for each object. So some objects you can pick, you can place somewhere else. And for other objects, you cannot pick, but they may have other properties. Like, for example, a refrigerator is something you cannot pick, but it's a holder or a receptacle in the sense that you can drop other objects into it. So there's properties, and there's actions you can take on any object. For example, a cup you can pick and you can place on a table. A refrigerator you can open. Any kind of compartment or storage furniture, you can store something into it, or you can retrieve. And then you'd have a transition model, which basically says, if I apply action A on an object O, which has a current state, what is its next state going to be? And there's an initial and a goal stage, which defines what the initial state of the environment is like and where you want it to get to. And a lot of planning problems are, in some way, they're cast again into a graph search framework. And there are a number of techniques developed over more than 5 decades, which solve planning problems efficiently as some form of graph search. And over here, what you see is a block stacking problem, which is perhaps one of the most commonly given examples of a symbolic planning problem. So you have a stack of blocks here, and you want to get to this particular goal state. And you have a transition model that describes which of these blocks can be moved and how the environment gets affected. There's a few considerations when you talk about a planning technique. And if we were to have a planning technique that is ideal, a best planning technique would be efficient, optimal, and complete. I'll go into some of these definitions quite soon. But in the case of indoor environments, you really have a very wide range of objects, and you can do a lot with each of these objects, and each of these objects end up having different properties. Again, some of these may be things you can pick, some of these can be things you can only slide, and some of these are just storage objects, so you can store other objects inside of these. And there's all forms of other task specifications as well. So your task could just be to bring an object, or your task could be to clean up my house, which is, again, it involves a lot of tasks with a lot of different objects. So for the considerations, we need planners to be efficient. So we need planners to work really fast in terms of wall clock time. You don't want planners to take hours and hours to come up with a plan of just fetching a cup to your table. And in some sense, you need planners to be optimal. So you want them to choose the best possible plan given your environment and not take forever to execute a plan. And you want them to be complete in the sense that if a particular plan exists, then your planner will find it. And now, so we talked about planning, and I'm now going to take a detour and talk about 3D scene representations. So there's been a lot of research into how we should represent 3D scenes, and a lot of SLAM literature kind of represents scenes as some form of a map. And these maps can be just point clouds. These maps can be meshes. They can also be very, very abstract topological maps, just like I showed in the map light video, where the map was just a bunch of intersections with a connectivity information. So in the last couple of years, I think this was Luca Carloni's group at MIT, and then at the same time, there was also I think Jitendra's group from Berkeley trying to do, or perhaps it was Stanford, a group from Stanford trying to propose this formalism called a 3D scene graph. And what's largely accepted as a 3D scene graph these days in the robotics community is some kind of hierarchical organization of an environment. So in this image, you can see one example of a 3D scene graph where you have a building and that building is divided into rooms, and rooms are further subdivided into objects, and then objects can also have some properties of their own. So each object will have some set of properties that determine how you can interact with it. And all of these levels are organized into a hierarchy, and having this hierarchy makes representing a scene very, very effective. So if you have a task for which you only need a part of the scene, you can only trickle down one part of this hierarchy and then reach one room that you care about. And this is why, like, 3 scene graphs, when they were designed, one of the goals mentioned 3 dynamic scene graphs paper by Tony is they designed it with task and motion planning queries in mind. So you want to be able to query this map or scene representation to see if you can actually solve a task and motion planning problem given a particular specification. So again, here is one example of a 3 scene graph. And in this paper, we kind of talk about scene graphs. The lowest level in the scene graph is an object, and then objects are grouped into place. For example, all of the objects that are on a particular table are grouped into one place that denote that table. And then they're organized into rooms, and rooms are organized into floor, and then you have a building. And connectivity across all of these, for example, connected room nodes imply that there is a path from one room to another. And then connectivities, again, or here from the rooms to the lower level, indicates that it indicates this room contains an object kind of relationship. And 3 scene graphs have already been used over the last 2 years in a few applications. For example, semantic path planning, like planning a path to one particular object category, or also object retrieval. So things like, can you fetch me a mug? And small scale task and motion planning problems, typically involving, I think, a dozen objects. So what's so far missing in the 3 scene graph community or literature is, 3 scene graph representations. They look quite cool. They're actually quite efficient in organizing an environment hierarchically. But can we now do very complex or long horizon tasks using these abstract or hierarchical representations? So they've been successfully demonstrated in small scale tasks, or like tasks that have a single goal, like find me this object. But what if we change the task specification to be more complex? And that's precisely what we try and do in this effort. So we've looked at a few existing environments, and because existing environments did not have too many buildings, we wanted environments that have a lot of buildings, and in each of these buildings, we wanted to see if they were amenable to creating scene graphs, and if they had an easy simulator and so on. So we ended up picking the Gibson environment because it already had a lot of scene graphs, and by far it had the largest number of building level scenes. So there were about 1,400 buildings in the Gibson environment when we started looking at dataset options. So what we first did was to build a benchmark of task planning problems over 3 scene graphs. So we took 140 buildings from the Gibson dataset, and for each of these buildings, we annotated plannable attributes. So we first had 3 scene graph information that had objects, places, rooms, and so on. And we annotated plannable attributes, things like, can you pick this object up? Is this object a receptacle? And what's the weight of this object, or like how many other objects can this take in, and so on. And we created 20 planning domains, and planning domains are classified into grounded or lifted. This is one distinction I want to make at this point in the talk. So there's 2 very broad classes of planning problems, which are grounded planning problems and lifted planning problems. In grounded planning problems, you have a particular, very concrete object instance associated with the code. So it'll be like, go fetch me my favorite mug, particular concrete mug from the kitchen. That would be a grounded planning problem. A lifted planning problem would be a slightly ambiguously specified problem in the sense that you can, it applies to anything in a category. So you can say, fetch me any mug from the kitchen. So lifted planning problems typically tend to be more, they tend to be harder to solve because you have a lot more choices here. And we take about, we take a good sampling of classical and learning-based planners to see which of them fare well and under what conditions. So there's a total of 18 planners that we evaluate over all of these buildings and over these different planning domains. And in just keeping up with recent trends in planning problems, we've defined a few task categories here. So one broad category of symbolic planning problems is rearrangement. And rearrangement, again, was a very recent multi-institutional white paper from a lot of robotics and computer vision researchers. And rearrangement is basically a task where you have k objects and you need to rearrange them into k different target locations. And rearrangement is actually a very general planning problem in the sense that it encapsulates a lot of different tasks a robot would do in just one broad construct. And we also created a slightly harder version of rearrangement, which we call courier. In rearrangement, the robot has to rearrange k objects into their target locations, but it can only carry one object at a time. So a robot will go to one object and then carry it and rearrange it in another location, and then go to the second object and so on. But in the courier, we have a robot that has a knapsack of capacity n, and each item has a particular weight in terms of the amount of space it occupies inside the knapsack. And the robot now has these stow and retrieve actions, which can use to stow and retrieve objects from a knapsack. So this is effectively embedding a combinatorial optimization problem within a simpler rearrangement planning problem. So you'd expect a courier to be significantly harder than a rearrangement. And there's lifted versions of these problems, which are, again, they're in terms of the goal specification, you don't have specific objects, you rather have classes of objects that need to be rearranged or couriered. So this is the main kind of table that summarizes some of our findings from the Taskography benchmark. And I'm going to break up some of these key findings so that you can make more sense of it. But before that, just the way you need to read this table is there are 6 domains shown in this table. There's rearrangement 1, which means you're just rearranging one object from one location to a target. And then there's a rearrange 2, rearrange 10, and courier 7 and 10. So courier 7 and 10 means you have 10 objects that you need to rearrange, and you have a knapsack of capacity 7. And not all of these 10 objects have the same weight. So one of these objects may have a weight of 5, one of these objects may have a weight of 1. And what you're optimizing for is you want to minimize the plan length. So you want to achieve the task in the least number of robot actions. And then you want to achieve it, you want to compute this plan in the least amount of wall clock time. So that's the time factor here, report in seconds. And then you want to have the highest success rate. So you want to have 0 failure rate, ideally. So first thing we find is there's, again, 3 classes of planners here. The first section here is optimal planners. And all of these planning techniques, they want to find an optimal plan. They want to find the best possible plan to solve this particular task. But because they always want the best possible solution, when the problem size grows really unmanageably large, they just keep recursing, they're never able to compute the plan because the number of branching factors is actually quite large in some of these domains, as I'll continue to show. So what this means is optimal planners, they actually cannot solve a lot of long horizon planning problems here. And in our experience, we just left them to run overnight and even for multiple days, but they still wouldn't converge. So that's clearly a domain where you don't want to be optimal. You probably want to be greedy and pick a satisfying solution, in the sense that if you get a plan that satisfies all constraints, I'll return it. I'll not worry about whether this is the best possible plan. So instead of a robot just being stuck at a particular point, deliberating infinitely, you'll actually get a plan much faster. And the idea is, instead of a robot waiting 2 days, you can probably take a suboptimal plan and still execute it in a reasonable time frame. So there's a lot of satisficing planners, and you can see that satisficing planners are able to solve most of these environments. But when you get to the really large tasks, so rearrangement 10, career, and so on, it spends around 3 minutes to 2 minutes to a minute just computing the plan. And this is not something we'd want, especially if you want robots to act fast. Then you'd ideally want to reduce this planning time as much as possible. So satisficing planner, they're quite slow. And importantly, they also have a lot of failures. So you see that the failure rates for most of these planners, they fail on about 50% of the problems here, or 90% of the problems for some of these planners and tasks. So you want these failure rates to be as close to zero as possible. So the other kind of planners we benchmark, so state-of-the-art learning-based planners, there's one particular approach called Ploy, which I'll briefly detail, but that seems to do really well in the sense that it plans much faster, within less than a second, and its failure rate is much lower, 20%. And then it also has a fair plan length. Its plan length is not too larger than some of these others. So there's like these three key observations here. And when we dig deeper, there's two solutions that we come up with for both of these kind of problems. And one kind of solution here, so this was again work by Tom Silver and Rohan Chitnis. This work, Ploy, this was the best performing approach in the table. So the last row, Ploy is the approach that you see here. So the key idea in Ploy is, if your scene representation has a lot of objects that are not relevant to the task, so they're extraneous objects, then they tend to eat into a lot of your planning time. So if you're able to somehow eliminate these extraneous objects, you can do much faster. And the way they do this is by training a graph neural network. And the graph neural network takes in the set of all objects and then the goal specification, and then predicts for each object, is this object relevant to the goal or not? And after this classification, they're able to come up with a threshold saying, I'm going to remove all objects that have an importance of less than 0.7, and then try and plan with only objects that are reported as important. So that tends to work quite well, but when the branching factor increases by a significant amount, so in our tasks, you'll see that the branching factor, the mean branching factor per action, it's about like 80. So for each state you're in, there's probably 80 new states you can go into by taking a different action. And there's this other like relational policy-based planners as well, which do not do well because there's a lot of branching involved. And we actually see that relational policy learning algorithms, they're not able to converge or produce solutions to even one of our problems in our domains. And we also tried learning representations from a sparse award by embedding a planner as a non-differentiable block into a reinforcement learning pipeline. But that did not produce good results either. So again, coming back to Ploy, Ploy was this approach where I mentioned they train a graph neural network to take each object in the scene. So you see all of these objects, and these objects are scored based on their importance to the plan. And they take the top k ranking objects and try and compute a plan with those top 2 objects. And if you get a plan with those 2 objects, then it's all good. But if you do not get a plan, you relax the threshold. So if the threshold was initially 0.7, you'd relax it to 0.6, and that would bring in more objects in the mix. And you'll try and see if you can compute a plan with these expanded set of objects. And eventually, at some point, if you keep relaxing this threshold is going to go to 0, and then you'll have all objects included in the mix. And if the original problems are solvable, you will end up getting a plan. But the key idea here now is, can we do this using very few replanning iterations? So when we get the first set of objects, can we ensure that those set of objects are sufficient for your task, instead of relying on a graph neural net scorer that might have some random noise that sometimes deletes objects that are not relevant? So with state-of-the-art planners, the issue is they have a lot of replanning iterations. So for a lot of these lifted tasks, they tend to have a lot more replanning steps. So you need to replan for 250 iterations, which means you need to keep relaxing the threshold about 250 times and keep computing a plan each time. So key contributions from the benchmark, we found out 2 key issues. And to tackle these issues, we find that you need to sparsify 3D scene graphs. So instead of planning on a full 3D scene graph, which is impractical, you need to sparsify these scene graphs so that you only retain task relevant nodes and attributes, and that makes for faster planning. And then the second key idea is you want to exploit the structure of these 3D scene graphs to reduce the number of replanning iterations for state-of-the-art planners. So we do this by proposing 2 techniques called scrub and seek. And I see that we are at about 12:45. So I'm gonna try and wrap up in 5 to 6 minutes so that we have enough time for questions. So the first strategy we propose is called scrub. And scrub takes in a 3D scene graph and a task specification. And then it starts working backwards from the goal. So it starts out by including all of the goal nodes and their properties in the 3D scene graph. And then it sees if these predicates are to be true, what other nodes should we include in the scene graph? And it keeps working all the way to the root until we're satisfied that all of the attributes and nodes we need for the goal are reachable from the root. So once we do that, this process takes only a few milliseconds because it's linear in terms of the number of nodes in the scene graph. It's just a bottom-up traversal where you're starting from leaf nodes and traversing to the root. So in the worst case, your 3D scene graph is already minimal and you retain the full scene graph. And that'll still just take 1 graph traversal. But for most tasks, we see that there's a lot of scene attributes or operators that are not essential to a task. And you can refer to the paper, or I'm happy to chat about later for proof that says for grounded planning problems, this kind of a scrubbing strategy is actually optimal in the sense that it'll give you a minimal scene graph, a scene graph with the least number of nodes and edges. So you see that if you actually scrub the scene graph, you're left with a much smaller graph, fewer operators and fewer state variables. And because you have so few operators and state variables, your planners become much faster. So in this case, you see that all of the planners that do not use scrub, so all of the planners that have a circle in here are the ones that do not use scrub. And the crosses are planners that use scrub. So all of these planners scrub the scene graph before computing a plan. And the idea is scrubbed problems actually compete or outperform state-of-the-art learning-based planners. You can see that in terms of the number of planning steps and the plan time. especially plan time drops quite a few seconds. In this case, about 7 seconds is saved. In this case, about 15 seconds is saved just by scrubbing. And we also show that once you scrub these scene graphs, you can actually get optimal planners to work. Optimal planners, which initially would not converge, even if you run them for days, would converge in a few seconds if you scrub the problem to retain only task-relevant nodes. But still, there's issues with scrub for lifted planning problems. So for grounded planning problems, scrub is still optimal, but for lifted planning problems, scrub tends to retain more nodes because of its conservative behavior. If you say, I want you to bring me a cup, then scrub will retain all cups in the scene, which is not essentially needed. Like it's okay if you just have one particular cup retained, and that will be a much more easier graph to plan on. So we also present this other technique called seek, which augments planners now. So scrub was something which had nothing to do with planners. It was something which were just prone scene graphs and it can be used with any kind of planner. And seek is a strategy we use with learning-based planners. And the three key ingredients of seek are, it'll first ensure that all important objects are reachable from the root. So when your graph neural network predicts an importance score for each object, a lot of the times you retain important objects, but you do not ensure that those objects are reachable from the root. And that's what causes a lot of replanning iterations. So what we do instead is whenever you predict an object as being important, you'll also retain the entire chain to ensure that it is reachable from the root. And we see that in terms of replanning, seek significantly reduces the number of replanning steps for ploy. So if you use ploy, you get 150 replanning steps, but when you use seek, the number of replanning steps is somewhere around 10. And yeah, so the key thesis here is for grounded domains, you want to use scrub to scrub the domain first. And if it's a lifted domain, you want to augment your learning-based planner by using seek because it'll leverage the structure of a scene graph and maintain reachability. So again, before I just jump to the final slide, there's a few known limitations for the Taskography benchmark. So we only support a fraction of tasks that are actually possible with 3 scene graph domains. So we take a big step towards providing really large-scale tasks compared to what exists in literature, but we still only assume fully observable environments and deterministic state transitions. While these are assumptions we share with a lot of approaches, this is something future work should definitely start relaxing and move towards partial observability, stochastic transitions, and so on. And we also evaluate planning at symbolic levels. So it's a symbolic planner in the sense that each action tends to have an equal effect. So one metric in the paper was how many actions do you need to complete this task? And if you would take 14 actions, not all actions are equal. Some actions are clearly more expensive than the others, depending on the kind of robot and the environment you're working in. So for general planning capabilities, you will also need to reason about low-level motion planning in addition to symbolic task planning. So at this point, Taskography is perhaps the first benchmark to evaluate how large-scale scene representations gel with modern task planners. And our 2 key findings here are you can actually scrub the environment. So you can sparsify the environments given a task specification so that you only retain all the nodes and edges that are relevant to a task. And that makes planning much, much faster. You can also get optimal planners to work on domains they would not otherwise. And you can also get off-the-shelf classical planners to work on par or even outperform modern learning-based planners. So hopefully Taskography becomes very useful in informing design of spatial representations. So how should you design newer spatial representations for task planning and so on? And at this point, I guess we only have 10 minutes left, but I'm happy to take as many questions as we can in this time.
Perfect. Thank you so much, Krishna. I would like to invite the audience for any questions at the moment. And you can write them in the chat or you can unmute yourself. Yeah. And I can start with the first question, maybe. So I would like to ask you, Krishna, and maybe this is more a general question. You call this a benchmark. And so I would like to ask you if you followed some guidelines for building a benchmark. How did you actually started, like the very beginnings, thinking about this process and trying to bring a solution?
That's a good question, and that's not often something we talk about in the context of just a research talk. So I think this is a good segue to provide some insight. So this effort started back about a year ago, and at the time it was like we wanted to see if 3 scene graphs were amenable to planning, and the first thing we did was look at a lot of data sets that existed and a lot of simulators and the kind of scenes they provide. And actually, during the initial phases of Taskography, we were moving around a lot of simulators and data sets until we found a Gibson to be the most suited. So we actually had, if you will call them, versions 0 or versions -1 of this benchmark on 2 other different data sets of, among the list that I showed earlier. But we figured that either they were not large enough in terms of scale, so they did not allow for us specifying enough problems. So we wanted at least, let's say, 1,000 planning problems overall of varying complexity, but some benchmarks did not allow for them, or there were other benchmarks which did not, which had a lot of scenes but did not have the scope for us to define plannable attributes and so on. So I think Gibson was effectively the third data set that we got to in this effort. And that's where we found, so we had a lot of design criteria in mind. We wanted to have enough scenes and we wanted those scenes to be large scale. So we didn't want scenes that are just rooms. There are environments which are room scale and which already have a lot of plannable attributes annotated. But the hard part there is you don't have a large enough hierarchy. So you just have objects, places, and room. And that becomes too small when you want to talk about planning and a scene graph. And we felt the scale of a building is where we'd be comfortable calling it a benchmark, because we're actually now talking about at least 5 levels of hierarchy. And then at each level in the hierarchy, there's at least different ways of connecting objects. So for example, you also need to reason about which rooms do you retain in the graph, because when you remove a room, you're also removing all rooms that are connected to it. So that was one level of, those were the design decisions that went behind, like choosing the data set and choosing the number of problems. And also the number of problems was also guided by how much training data would a learning-based planner need to efficiently succeed in a particular environment. And we actually ended up having 5x the amount of data, so that if people wanted very large scale planners in future, they have more data than what current planners need.
Yeah, that's a great insight, actually. Thank you. Any other questions?
I can have a question. Thank you, Krishna, for the talk. So I don't know much about task planning and 3D scene graphs, but it seems like the majority of the work that you talked about works only on simulation environments. Are you aware of of interesting work that also does this in robotic platforms in the real world? Because it seems like a difficult task to do, especially considering all the hierarchy that you are considering in your simulators.
Yeah, that's a really great question. And so, like, to give you the short answer, Taskography, yeah, it is still at the symbolic level. So you only do task planning in simulation, but there are approaches, or there is now promise to believe that this can soon be translated to real world. So one big reason is 3D scene graphs. Again, Luca Calloni's group from MIT is doing a lot of work in trying to build scene graphs from real world data. Can you build these? And in fact, their Chimera pipeline and library, they are building scene graphs from real world environments by applying visual inertial odometry techniques and then semantic segmentation and so on. That said, it is still offline. So these 3D scene graph representations need to be built offline. And in parallel, there's work, again, presented this year at Coral, which tries to recover symbols from perceptual inputs. So one other problem is you don't just want a reconstruction of the scene as a static mesh and segment out objects. You also want to figure out what kind of properties these objects have. So there's some work on trying to recover these object properties or potential object properties from real world perception. And as in the robotics community, there's a significant emerging trend of task and motion planning. I think Leslie's group at MIT pioneered task and motion planning for a large number of years now, but at this point, we're beginning to see promising results, including one approach that I mentioned about early on in this talk, which does task and motion planning using scene graphs in the real world. But the drawback there is that at this point, they're only able to scale to a dozen objects. So there are scalability challenges that need to be overcome. But that's where I think some of the ideas from Taskography step in. So whenever there's scalability issues, if you explicitly reason about all the possible choices and which of these choices are relevant to the task, I think there's a nice fit as to like taking real world or realistic 3D scene graphs and then sparsifying them just to the extent that is required for a task, and then applying some form of task and motion planning techniques on it that work for smaller scale scenes. So there's still a few hoops to jump through. This is like we're just scratching the surface, but this really seems to be the right time in the sense that all of these different efforts from different labs are coming together.
Okay, thank you. Thank you so much for your answer.
Krishna, there is a question in the chat from Marcos Pereira. I'm going to read it for you. Thank you very much for the interesting presentation. I would like to know if those methods depend on having a pre-built action planning graph, or if they also work on building the action planning graphs. How are the action planning graphs generated? Does the state space explosion problem occurs? And just to keep it in time, if you could wrap up in about like 30 seconds, 1 minute answer.
Sounds great. So yeah, in this work, we assume offline planning. So we have this closed world assumption, which means all of the attributes and transitions need to be defined beforehand. But there is work from Luca Calloni's group. I'd like to point you to the Chimera package to kind of see if how these can be generated from real world data. And for predicates as well, there's newer work I can point to. Hopefully this is still just on time.
Yes, thank you. Let's thank the speaker. Thank you so much, Krishna. If you would allow me just to close the session and share my own screen. Perfect. So just to wrap up, oh, sorry. This is not what I wanted to share. So on the next session, we will have Professor Tony Belpain, and we will actually take a break right now for holidays. So we will join again on January 7th. We want to thank our sponsors again, Animatas and Semyu, for supporting us. You can also support us by buying us a coffee, which the link will be on the chat in our website. And happy holidays, everyone. Thank you so much again, Krishna. And yeah, have a good Christmas and New Year.
Thanks. You too.